I'm Liz Beckman. Welcome to this part of the CT at 50 celebration and some key highlights of the history of the development phase of CT. Looking at the early 6 years, taking us from 1967, when the first idea of CT came, to 1973, the point at which CT was becoming accepted and an unstoppable revolution. By late 1973, there were CT scanners installed in 10 hospitals in different parts of the world. By this stage, it had become an unstoppable revolution. Over the next few minutes, we'll have a look at the timeline of some of the key stages that the process of developing the CT scanner went through. We'll look at some of the challenges and hurdles, and importantly, the key people who helped to overcome them. We'll also look at the very key area of where the whole project may have failed. And we'll have a little look at the challenges of the fact that it was done with such limited funding, but was dependent upon the improvisation and the great collaboration of the team working with Godfrey Hounsfield. This chart splits the development project into its 5 key stages, going from pre-contract right the way through to the rollout of the clinical scanners. The red bars show some of the major tasks and where they were in the timeline. Their label is down the left-hand side, showing them from when the early work of the simulation and the patent work, through discussions with the Department of Health, the various lathe bed models, the development of the original clinical prototype, the first scans at Atkinson Morley Hospital, and the rollout of the 9 hospitals after that. The blue bars identify the key people and when they were heavily involved in this project. The first of the project stages was the pre-contract stage, and it was in this phase that Godfrey solves what he called the 3D reconstruction puzzle. And also it was now that he realized that the best application for his 3D reconstruction puzzle was in medical imaging. But the problem was that his employer, EMI, were not in that field at all, and they had no interest in funding a project in medical imaging. So the challenge for Hounsfield was to find an external source of funding. To do this, he had to prove that his image reconstruction worked. He had to do this so that he had something to convince potential funders. He also had to get patent protection, because he didn't and couldn't risk the fact that if he showed his idea to a potential funder, they would just take the idea away and do it themselves. The second phase was the laboratory tests, which were carried out on this lathe bed prototype. Well, you might ask, why a lathe bed prototype? Surely no one would build a prototype using the base of an old lathe, unless they were very short of money and very good at improvisation, as Godfrey Hounsfield was. This photo shows the lathe bed, and the blue arrow indicates the direction of the linear motion of the system. In this prototype, that linear motion was driven by the screw in the lathe, and that drove the tissue sample, the brain, across as the X-ray tube and the detector stayed still. In the next slide and video, if you watch carefully, you will see that motion. In this video, you can see Stephen Bates and Peter Langston with Godfrey and the lathe bed. and you can see the brain specimen moving across the gantry. Then the small amount of rotation of the brain sample. Godfrey certainly seems very pleased to see that the lathe bed is working again after a gap of about 7 years. It certainly looks as though it was put together at the lowest possible cost, but Godfrey was always determined to maximise the image quality. The lathe bed was used to scan various pieces of tissue, bone, brain in formalin, as you just saw in the video, and also an abdomen of a piglet. Those images were sufficient to convince key early medical members of the team that it was worth developing a clinical prototype. So this was the next major phase. These photos here show the scanner and viewing unit. In fact, these photos are of a slightly later unit, but they are almost identical to the prototype. The fourth phase was the clinical trial at Atkinson Morley Hospital in Wimbledon in South London. Through the development phase, Godfrey Hounsfield had collaborated with Dr. Jamie Ambrose, the radiologist at AMH, on tests on the lathe bed, and Dr. Ambrose had been involved in the design for the clinical prototype machine. On the right-hand side of this slide, you can see two clinical images. The one on the left, numbered 200.2a, is the famous first CT scan. Interestingly, this was done at a matrix of 160 by 160 pixels. In comparison, the picture on the right, 215.1a, another early scan, I suspect patient number 15 by the numbering system there, was actually scanned at an 80 by 80 matrix, and you can actually see the individual pixels on that scan. The key thing here is that the spatial resolution in CT was in fact a step backwards from traditional X-rays that were available at the time, but the contrast discrimination was greatly improved. On this slide, you can see some of the first publications and awards that were received for the invention of the CT scanner. In April 72, the announcement at the BIR's annual Congress in London. Then in May 72, the announcement in New York. And the first award in November 72, the award of the McRobert Award, for which Godfrey received a payment of £25,000. In comparison, the chairman of the multinational EMI that Godfrey worked for, Sir Joseph Lockwood, was only earning an annual salary of £23,000 at that time. This slide shows the order in which the first 10 CT scanners were installed in the world. After the first in Atkinson Morley, there were 2 more systems shipped in the UK, one to the National Hospital Queen Square in London and the second one to Manchester Royal Infirmary. After that, 2 to the USA, Mayo and Mass General. By the end of September 1973, there were 10 systems installed and had done their first clinical CT scan around the world. 4 in the UK, 4 in the USA, 1 in Canada and 1 in Sweden. Like most projects, there were huge hurdles and challenges to be overcome in the development phase of the CT scanner. Right from the beginning, when the reconstruction had to be proven using simulated data. Here, Stephen Bates was a great assistance to Godfrey Hounsfield, writing the computer programs for him. This proof was needed in order to raise the funding for the laboratory test, then to actually do the laboratory tests, during which there were a huge number of different problems to overcome, from optimizing the reconstructions to working out how to sample the data, and also to getting hold of the specimens to scan, and then identifying key medical collaborators who could actually see the benefits and potential for the system. Then the very difficult hurdle of raising the funding for the clinical scanner. Discussions on this went on well into the development phase. The key funder, the Department of Health, didn't have money for R&D, but they did have money for hardware. So it was agreed that they would sign a letter of intent that if the clinical prototype worked to specification, then they would buy 4 scanners. And this was enough to enable the clinical prototype to be developed. Then there was the hurdle of developing the clinical scanner. Here, a strong collaboration between Godfrey Hounsfield and Jamie Ambrose was essential. Hounsfield providing the technical and scientific know-how, and Ambrose feeding in the medical and patient needs. And then on to the clinical trial and the rollout. It was in the rollout that Matt Gollifer did an interesting piece of work. Initially, it had been assumed that CT data would be sent to a central mainframe, one in each geographic area where the scanner was, because at the time mainframe computers were far too big and complicated to have one in each hospital. Matt Gollifer was asked to set up the communication data lines between the individual hospitals and the central mainframes. Mac had just been working on a project using mini computers, and he said, "Why don't we use that instead?" And that was a major step in making the CT scanner practical for hospitals around the world. Instead of getting results the following day, the hospitals got the results while the patient was still in the department. The development project of the CT scanner could so easily have failed at any stage of the hurdles we have just discussed, or at many other points. This included the area of working on the reconstruction that needed to be so accurate and fast. Credit here must go to Godfrey Hounsfield himself and to Stephen Bates. Stephen listened so carefully to Godfrey and translated his ideas into practice. He also helped Godfrey to refine the ideas, optimize them, and make them as accurate as possible, and also as fast in the computer as possible. Crucially, to use absolutely the last bit of photon noise in the data as could be achieved. The funding of the lab test could so easily have been refused at the time. Everyone in the medical imaging field was striving to improve the spatial resolution in X-ray images. So the majority of people in radiology and industry at the time would have considered funding this project as insane. They were against any loss in spatial resolution. The credit here goes to Cliff Gregory, who was at the Department of Health and whose budget was being used, and also to Godfrey himself, who managed to convince people that his concept would work. Also to Frank Doyle, who acted as a peer reviewer and recognised that this was a worthwhile project. It is interesting that at around this time, Siemens had had a project investigating a similar concept, and this was later mentioned in a paper by Walt Robb of GE in around 2000. Siemens had spent a lot of time and money, and they concluded that the concept was 10 to 20 years ahead of its time, because to reconstruct an image with a spatial resolution that they regarded as essential would need the power of the largest computer in the world at that time. That shows how easily the funding for Godfrey's project could have been rejected. Funding was also an issue for the clinical trial. Here, in addition to Cliff Gregory, Frank Doyle and Godfrey, credit should go to Louis Creel, Jamie Ambrose, Billingham and Gordon Higson. The latter two non-medical people, Billingham was Godfrey's immediate superior and he ran the EMI's central research laboratories. Gordon Higson worked alongside Cliff Gregory at the Department of Health. They were also very supportive and helpful at this stage. It is perhaps interesting that the three people who probably had the most to lose at this stage were Godfrey and Billingham, both of whose jobs would have been on the line if the project had failed, and Cliff Gregory, who was at high risk if the project failed, since he was spending public money. Another key risk area, because there was so little money, was the clinical trial itself. This had to be right first time. If the clinical trial hadn't worked, then there was no money to improve the scanner or to do more research work. It had to be right first time. It had to detect tumours, hemorrhages and cancers. It had to meet the relevant safety and hospital equipment standards. And it had to be comfortable for the patients. And this whole area was a really great credit to Godfrey Hounsfield and his collaboration with Jamie Ambrose. Many of us really love this cartoon, which was drawn by Tony Williams, a lead mechanical designer who worked with Godfrey Hounsfield. While it might be a slight exaggeration and might imply that the CT scanner was made from scraps, it certainly does highlight the fact that so much was achieved during the development phase by Godfrey Hounsfield using his great ability at improvisation. He certainly achieved a tremendous amount with very, very little money, but he did have great collaborators, people of high caliber, including Jamie Ambrose, Frank Doyle and Louis Creel. It's also interesting that all of the R&D and the building of the first clinical prototype was achieved within the Department of Health funding of £90,000. That was a very small budget, and it's absolutely extraordinary that it was achieved for just that sum of money. After all, that was only about 50% of the cost of the CT scanners sold a year or two later. I suppose that is rather like buying a car for £15,000 and then learning that the entire budget for the development of the car model was only £7,000. It is certainly amazing that Hounsfield managed to achieve the pioneering work of the design and development of the CT scanner on such a small budget. Thank you for watching this whistle-stop tour through some of the key milestones in the development of CT in celebration of CT at 50.